So we already solved these challenges. Today we are looking at Apple Store. Tom Cruise rooted Galaxy S5 200 points, but we need you to jailbreak an iPhone 8, the server, Apple Store, and Lipsy. So this should be this should be all right. We have our own. Let's download it first. Apple Store, uh, x86, dynamically linked, not stripped. That's great. So then we have Lipsy. I think this is the same as last number. Yeah. Then we're gonna look at an Apple Store. We have some menu, my read, add, checkout, cart, quite a lot. Let's see if we have malloc. We have malloc. We have free. We don't have free. So if this is a heap challenge, which seems very highly unlikely that you don't have free. Okay, so this is main. You signal, set up a handler to timeout, just times up. You have alarm for 60 seconds and you mems it on my card. My card is in. Alright, my card. Call mems it on with 10 bytes, writing 0. You call menu, Apple Store, and remove list checkout. You call handler. There's a jump table, case 1, list, add, delete card, checkout, and then you have something. It's not a choice, idiot. Thank you for your purchase, and then you can exit. So this is case 6. All right, so first look at the list. This is nothing, it just lists some devices with printf. All right, then you have add. Okay, add has some options. Okay, let's see. Ask you for a device number, converts that to an integer, and that means you'll have to choose between these devices. And once you choose them, calls create with two parameters. One is, I think this should be the price, and this is the name of the device. It goes to create. Once that is done, so and then insert. So whatever is returned from create is used to call insert, and then you print out that you have added something on your card, and then it returns. Stop doing that, idiot. I think that should be there. Yeah, yeah, okay. So we have, let's look at insert. Quite small. I think we should look at create first. So what create does is fixed size malloc. Return values then saved. So create had two parameters. One of them was price and the other one was the string. So both of these are then saved inside the structure at different offsets. and a printf is called to the buffer. Alright, so that means create allocates some space as in hex 10 bytes. For x36 that's 4 into 4, 16 bytes. So we have two empty slots that we haven't figured out what. In insert, what it does is it uses the value from this pointer if it's 0 or not. If it's 0, okay, EBP plus var4. We only need one parameter, which is r0. So what we are doing is dereferencing arg0 and moving something inside that. Sorry, to our var4, which was my card, and then you have copying it back into your arc. Okay, here what you do is, okay, this is a loop. So it moves something from here, then it moves there. Dereferences at 8 offset and uses that into the local copy. So I think this looks like a linked list of some sort. Let's verify that. So this function is basically you create some offset malloc, then copy it to var_c at offset 0c and 8 just 0 is copied. At offset 4 and 8 you have copied second argument and the price. So we have we have the structure that's there. Then we have delete. Yeah, and we have cart. I think they should just, yeah, they should just print out. So if this is a linked list, so let me check your card. Based on that decision, you either go here or go here. Canary check in the side. Card is started 28 compared to 0. Then EX at offset 4 to ECX 0C. Whatever is at offset 4 is used as uh, so there's one counter that was set to 0. Offset 4 is added, so I assume this should be the price of the item that we have added, and then it should move forward. Yeah, so here at offset 8 we have the forward pointer. So we still don't know what is there at offset 12, which I think we saw it here was using offset 12. 4. Okay, I think this is the okay, it's a doubly linked list. All right, so kind of have the structure. Let's directly move into that. So let's call it struct item. We have a star name, then we have int price, then we have struct item star ft. We have struct item, then we have a char name, then we have int price, struct item ft and pk. This should be all right. Now what create does is create returns a pointer for that this let's cast it. Yeah, so 3 v3 is also the same. Yeah, second is your integer price. Let's rename that. Why is not working? So this is char star, this is int. Yeah, this looks better. So you have a malloc of size 10 now, which is the size of the item. Then you have v3 equals v2 copies of the pointer. Price is updated from the price, and name is updated with the name from here. Probably ASPrintf is used. Let's see what ASPrintf is. Print to allocated string. Okay, so it automatically allocates a string for you. So that is handled there. Alright, so once we have that, we have v1 is automatically casted because we changed the type, I think. You have printed, okay, right. So insert has been, let's also update this. Yeah, so I is moved forward, I is equal to I forward as long as I is there. You have at the last, you add and update forward for the last second last node and the last node back. So this is, I think, link, you link a double links node into the list. All right, so insert is done, should be void. All right, we have add done, then we have insert create my list. The list is done. Menu, there's nothing to do. Let's look at delete. So in delete, it asks for an index. So I assume my card because at insert we use the 0th index as my card. So my card should be 6 8 and 7 8. So this is a part of my card. We can, I think, let's cast it. Then when we go to delete, you can cast it to pointer. This makes more sense than that. So v2 starts with mycard.ft, and based on the index that you provided, that is this. So let's name it. So based on your index, if it matches, you have current pointer ft and current pointer bk. So this is the next node and this is the last node. So last node's forward is pointed to them. So this is like yeah, this is like unlink, normal unlink, nothing verified, just unlink. So once you have that, you keep an index of the, yeah, that's it. You just move forward with the ft pointer. You don't need to actually maintain the back. So I think then that's done. Let's look at the timeout is there and you have checkout. Okay, checkout is go to cart. Cart is you start with this, you print out the name and the price, you keep adding the price, let's call it final price. So you return final price, which is here, and if final price is this, then something is being done here. Okay, so what is done is if final price is some number, I think it adds an iPhone 8 for $1. Yeah, so insert is passed as okay, but where's v2? v2 belongs to the stack. Okay, this. Okay, so let's make it. Yes, that should not be an issue. So if your sum of all the devices is sum of prices of all devices is 7174, one device is automatically added, and in that case you get a stack inserted into your stack variable inserted into your linked list, which is just malloc objects. Let's see. Then we have puts want to check out maybe next time. So that means it won't let you check out. Let's go to main recipe. But you can exit when 6 is done. You won't be able to check out. Okay. So here in this case, this object that we are adding to doubly linked list belongs to the scope of this function checkout, and this checkout is only called from the handler function and nowhere else, but it's in a loop and we can return to this function. and we will have a reference of that memory which was the frame of this function in our doubly linked list. So this looks like use after return. I think that's what it's called. So you're using a frame of a function, you are using a variable from a frame of function which has already returned. So similar to use after free, this should not be done because once you are back in the frame of this function, you can call another function. Let's say we can call list, or list there's nothing. We can call add. It has some bytes of some of its stack space, which will overlap with the frame of the layer function called, and you will be able to change the values. So in this case, what options do we have? We can call all these functions. We can call puts, card, delete, add list, printf, flush, my read. Oh, my read, we did not check it out. So my read is, yeah, you have above. Okay. So I think this does not take that much stack space. Let's look at where the offset is. So this is ESP plus 18 or EBP minus 20. So we are at that point will be negative 28 bytes over the stack. So we need at least control over that. So in that case, this does not give us that much. Printf is mostly, and this is, I think this is a reference from the GOD. Flush is we don't control anything. My read uses a stack variable which is allocated in this functions frame, so that too is out of exploitation attempt. Add, let's look at add. So in case of add, we have one C space here. Case of delete, we have 3 8. So delete has quite a bit of space, and it uses my read to end pointer, which is kind of at EBP minus 22, and we want to control contents at EBP minus 20H. Okay, and we have card. Here also you read, I read at EBP minus 22. So that means we can use this delete and card functions, and maybe this add too. Yeah, this add to, when we once we give input inside this is x 15 bytes between. Is not these variables overlap. This is v1. No, they won't. You have c here and 22 here, so that means you have at least four of these, and you have 16 of these. No, they don't overlap in this case. Yeah, but we will be able to overlap with this case v2 will start taking 1 minus 20. Yes, so we can give this a try. Okay, but wait, that only gives us control over the values of that node. Once we have that, we can use the unlink function here, unlink feature, to trigger two arbitrary overrides like you have in the unsafe unlink attack on heap. So this might give us a good primitive to override something. So the assumption is that we'll need two addresses which should be both be RW. Let's look at it once. Okay, actually to hit that we need to solve the problem. It was in checkout. So we need to get to 7174. The prices are, that means every price is ending with 99 and you have 74 here. That means we need 26 devices at least. So the smallest price is 199, so let's say 26 to 1. We get 5174. We want is 7174. That is 2k short. So we can use a device from here. So we want it to be okay. So 26 into 199 is all right. We need 2000 more. So 20 of these we can make 299. So 20 into 299 plus 6 into 199. Yes, this sits perfectly. So we need to add 26 devices. I can't do that manually. Let's write a script. Oops. So we have context.binary. This will set the context.arch for us. Then we need to define that what is this? Add. So let's add. We can call rdx. Let's look at that. First we need to send one. So need a start receive until this. Then no, we need to send actually two to add. All right, so two. Then once we have that, send the number, and then we have two lines. Okay, so let's also copy that. This is idx. Then we have once we send that index, we have two lines. I think that should do. So for now, let's start by for I in x range 20. So 20 times we add 2. And then for I in x range 6, we have add 1. and then we get let's add interactive. Is it all right? So we have process, then we do that, do that. All right, so let's do that. On line 2, on line 1, odd. Do we still have that? Why do we have that? I don't know. Oops. Okay, so now we can say list your shopping cart. Say why. I have 26 devices, I think that should do. And we can check out from 5. Say why. Yes, so that has been added. And what we were trying to do is we should try to go to handler and then call card and then write a lot of bytes here. So to call card, you do 4. When it asks me this, we can say give me all of it. I think it crashed. Yes, it actually crashed dereferencing this address. So we can attach GDB. So GDB.attach. That should be all right. Now once we do that, we will continue. We will go 5 and it will ask me for that. Maybe next time. Now that has been added, we'll go 4. Say y and a lot of a's, and then we have a crash. So crash happens in printf. All right. So in this case, crash happened at printf. Which was here. I think it is trying to print the current, and we overflowed the name into the name. It gave us control over the structure. All right, so this means we can deref arbitrary pointers and leak stuff. We can go around and send a cyclic pattern of hex15, that is 21 bytes. We can click 20 because 1 we already pushing. I think it should be at offset 1 or 0 in this case. So first we go 5 and it says y, and we go 4, it says y and this, then it overflows, and then we Yeah, so this is at offset 1, 6161. So we overflowed from here. So since we have that, what I'm gonna do is let's write a function for what other functions have we gotten. So this time we used checkout. So let's do that. We can say def checkout. Checkout doesn't need anything. It's just mm, actually, let's copy both of these. Or so checkout is option number 5. Once we have that, you can say here we'll send y, and then it will print out. So you can say receive until total and maybe receive until time. I don't think we need that for now. So checkout is then we have added. You want to list? Mm, so to list, we need a function. Let's call it list items, and we should get that string. Call it choice. So list is same. It will print out the card for us. So we get that, send 4, and then we get a y of that. So in that case, then it will print out the card, which in that case is so the moment we are leaking, it should have 26 devices, 27 devices. So let's change that. So in that case, it will say 27, and then Yeah, so now what should we do is first we should check out and then do list items. We can call it y slash x. Check. This is that. I read into buff. Okay, it only checks one byte, so this could be anything. ELF is equal to what we're trying to do is we're trying to leak GOT address of puts. Do we have puts? Yes, we have puts. No, actually this was it's back. I think this should give us enough control over the structure. We had 15 bytes. There's 21, so we use 2 here, and then we are using 16 here. Okay, all right. So we have full control. Did we miss? Okay, we did miss. What was the structure? Oh, nops, 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 nops. It dereferenced. Yes, we did get something interesting. Let's try to verify that. Mm, Done. In this case, it will return the string pointed by the name, the index which we already have used. So yeah, you're not needed at all right now. Once we have that, so leak is equal to this success x of u32 of oops leak. I think this is what we need. Let's first continue. We have this here. Sprint puts. Yes, so we are able to leak stuff from the temporary or let's say last magic or hidden iPhone it added to our cart. Now to get a right primitive, we need to have, so we have already have an unlink primitive present here. So in this case, the index that you give, let's say here the index that we're giving is 1, so it will iterate to the first index using forward pointers, and then it will copy value from that index to the FD, and so kind of, yeah, standard unlink operation. So we can go ahead and try with 4141. Let's see what kind of uh, so instead of list, we can use the same myRead and nptr to control the structure once we deref, and we'll provide the that index to this one. So in this case, mm, no. We'll store, we can say remove, and it will ask us for item number. So here we maybe say, let's say 1, then that's it. Okay, so let's change that. We have del item, you have choice. Instead of 5, we say, instead of 4 we say 3 because of remove, then you send the choice, and that's pretty much it. All right, so what we're trying to do is trying to delete item number 27 in this case, because we have a control over that, and then say a into 0x10. Yes, let's try doing this. Yes, so as expected in delete, add this offset. So this is the unlink operation, the checks that we'd had. So it used the address from the corrupted item node, and it tried to copy edx there, which is also in our control. So this is a controlled write. So the address is what you control and the value you control. But the tricky thing is that then we are doing the same thing at this point. Here, so we'll be doing that backwards. So the FD and BK both need to be writable locations, so that is a little tricky for us. So what instead we want to do is we have leak of the libc, we have address of system, but what we don't have is if we patch GOT entries with address of system, the system is usually mapped to an Rx location, not RWX. So in this case, system will be somewhere here on this page. And since this is an unlink operation, both of those sections should be uh, in our control, or let's say should be at least have RW. So which in this case we only have this or these address. So only this address that we know of right now, and from the leak we got address of, I think this, we also have this. We can overwrite, I think, malloc hook, but that still should change with an address that belongs to writable location, let's say this. So this is kind of tricky. One option that I can think of is, let's have a look here. Okay, yeah, so we can leak, what we can leak is mm, we can leak the stack value using libc.environ. Which in this case is this value, which is ff2a5tc. So once we have leak from the libc, we can use it to control leak, and we get a leak from the stack. So what this gives us, we then have a control over stack to some extent. We can use that to, all right, wait, let's give this one a try. So we can abuse the leave instruction here. So at EBP usually have the old saved EBP written onto the stack, and this goes on. So as you can see, if we do BT, we have 1 2 3. So this should be the kind of the return for main. So you have a chain of pointers written at EBP, and once you return from a function, you usually call leave, which is kind of gives us control over EBP if we change the saved value of EBP. So we can use that as a pivot to actually move to, or first we need to write a rob chain somewhere. Mm, so in this case, what should be a rob chain is, we did not check, do we have, okay, we have partial railroad. So in case of partial railroad, mm, 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 we can pivot directly over the GOT. Since we have stack control for handler, we can change EBP for this function's frame, or So the control is over this function. We have control over, once we have delete, we can change EBP for delete, which is this value, and using this, when we return to this functions frame, which is handler, uh, we will this functions frame will overlap with our GOT page, and we have my read relative to ESP in this case. So no, my read is actually relative to EBP. So that should give us control to the pointer of this value, and we can then overwrite it with our control values, and then we A to I will be called. So this means is, first we pivot to the GOT using patching the leaked EBP, or patching the EBP value here using the leak from the environ, and then we use this my read to control the GOT table, and once we call A2I, we should be able to land in our popular in our code, or let's say system in this case. So A2I has one parameter, which is EBP plus NPTR, which is the place that we control. So that should give us enough control to actually write over the GOT table and change this to bin sh and change A2I's GOT entry to system. Uh, this sounds a little bit tricky. Let's go ahead and leak some values. So do we need to, will this library run as LD preload? That we need to verify. Oh no. So right now this library doesn't run in my, I need to start a Docker system. What I can try instead is, since we are able to leak arbitrary values, we can leak the stack from the FD pointer of the 26th object that we have here. So this object's FD will point to the stack's frame. So we can leak this value, and then we can verify uh, what items are, or the stack address. So how we do that is, here we have 27 casted. So to change that, so what I do is, I will start removing item number 1. We'll remove it 25 times, or let's say 26 times. Once we have done that, the first pointer on the 0, that was my card. In this case, let's go to delete. So my card, so that the pointer there will be on from the stack. So I think that we can leak out without using the current libc, or change libc for now, or actually we only need to, okay, let's use the environ as it is. We have, oops, we have this, then we delete this. We say Oh, we have libc. We leak puts. Puts was the first 4 bytes unpacked. Once we have that, environ should be puts minus c dot symbols of puts plus libc dot symbols of environ. So using the same primitive, what I want to do is want to leak this value here, and 'alright. So we have a leak of this value, and this actually starts to point at our environment, and our current EBP is this. Oh, 260. So our current leak, mm, FFCF49C is okay. So we have EBP. So what I want to do right now is let's go ahead and give it a test. EBP is and I want to change mm, so this is not needed. We can say we can keep it same. It's pointed to a value address, and then I want this um, So in this case, it's so EX is somehow we have lost control over EX. Why is that? Oh, we actually needed 16. Right. Alright, I forgot it was 16 bytes. We also have a price right there. Yeah, so whatever is at offset this, that it will be written to this plus 8, and whatever is at offset this will be written to this plus 12. I think that's what I make out from here. Hmm. So what I want here is on the list of GOT table entries, and I want that to go there. First one is we have a control over read, and at this address plus 8 we'll be able to write. So what I'm gonna do is I'll do -8, and now here this address plus 12, so I'll say EBP minus 12 should be the packed. I think this should give us control. Yeah, so this is all right. We look at our EBP, it crashed somewhere else. Where did it crash? Give me a backtrace, please. We need to set a breakpoint at the leave of this function. So we have overwritten EBP. Our EBP value has changed. Now we look at GOT. We have overridden read, I think. It is trying to call read. Yes, it is trying to call read. And this call will override the read. So we do not need to corrupt the entry of read. What we need is later we'll be calling a2i this function. So yes, printf is alright, memset is alright, and libc start main is alright. We can corrupt this entry. Think so. And this should give us control over the GOT entry of a2i itself. Let's change that. So the breakpoint is hit. Printf is alright. Flush worked. Now it is waiting for our input. I'm gonna send this 234 1234 1234 1234 and 1234. So now we have yeah, this is good. So the first parameter to a2i is actually the start of our input string, and if we look at GOT, we have oh, why are we still changing? Have I not saved this? I think we need to move. So we have only overwritten after that read, but we still have overwritten over this value. So this offset is, so what this is using is current EBP plus minus 22. So whatever your current EBP is, this value 20 minus 0x22. Yeah, so that's why we are overflowing or we are writing from here. So what I want this to be instead is so our EBP value is GOT entry of start main. I want it to be plus 22. So what this gives us is we will be overwriting over these values, but a2i will still be calling. No, we have 21 2 3 4 5 that is just outside our, so let's reduce 4, and this will give us control over a2i and the string that we are using. So I think Now if we go to A to I, yes, so do we have GOT control? No, we still, what is the EBP value? Need to move this towards there, not actually. So this plus 8 will be written there. Add this plus 8. Be writing this. This is going to be a bit tricky, I think. Yes. Yeah, so this is what we needed. So we control the first parameter to A to I, and what we also control is the GOT entry with the fifth entry. So what we are gonna do is instead of sending this, we do we send first we send slash pen slash sh. So this gives us 8. So slash pen is 4. This is 4 and this is 4. And then we send, so we have already sent these many bytes. Then we need to send x into 8, which is chunk. We need to send address of system. Now what this gives us is system is equal to puts minus 0 symbol of puts plus libc dot symbols. All right, system. I think this should work. Yes. Let's verify. Yes, we have overwritten with slash pen slash sh, and then we have this. Yes, this should set follow fork mode parent, and then we clear all of these and then we continue, and then we say pwd. Yes, this works. So we need to change libc. This is slash libc dot show file, and then we go to process. We Mm, why are we waiting? Oh, we're not waiting. Okay. Yes. Okay. So that's it. So this challenge was, so the bug was quite simple. The bug was that it is using a local variable to insert to the linked list, which was, I think you can check out. Yes. So a local variable was referenced into a W linked list, which was then later used as at in different functions. And since it's a local variable, most of the times we usually have control over the stack space. In this case, that was using a read. So I think this read is made specifically in that way that although it needs a single byte, it is using 21 bytes to actually read into the buffer, so that it gives us control over the content that we have in this stack frame. So this is so if we return from this function and we go inside this function, we have control over the stack frame of the earlier function because the variables will overlap. So classic return use after return. So once we have that, using the structure that we formed, we found out that there's a doubly linked list in place. We can use unlink feature to get arbitrary writes over both ft and bk, and similarly using the dump cart feature or write cart or list items, whatever, we will be able to leak arbitrary pointers since we have control over the description or name of the item. So this gives us a leak over the libc. Using that leak, we leak item from the stack. And using the leak from the stack, we pivot to the GOT table entries and we override entry of the A to I because it only takes one parameter, of which the control was uh, there because we were pivoting inside the function frame of this handler function, and the first parameter that was passed to A to I was based out of EBP. So the pivot was that we changed the saved value of EBP using the leave instruction that is usually there in the function. And using that pivot, we control this EBP and control the values passed to our functions because local variables are usually EBP referenced. So that gave us control over the GOT table and the variable or the first parameter passed to the function in one go. So using that, I called system bin sh here, which we can see, and that gave us full control. I think the challenge was quite tricky for now. Let's see how. So it has 559 solves, which is quite a lot. Uh, Next one, I think this is a new challenge, has 514 times. So overall, great challenge. Got to learn quite a bit. See you next time.